Okay. Can you hear me? Okay. Uh, Hello, everyone. My name is Huang Chikun, and I'm honored to be able to share my work here. The topic I'm going to share is optimal charging site recommendation and scheduling for electric vehicle considering user price sensitivity. Today, I would like to talk about six parts. The first part is the background of the electric vehicle. The second part is the problem and works. The third part is um, two-level models. The fourth part is case study. The fifth part is conclusion. The sixth part is future research. So, with the development and an environmentally friendly society, the numbers of electric vehicles is rapidly increasing. Due to their low carbon and environmentally friendly characteristic, the diagram on the right simulates a realistic charging scheduling scenario, and with green arrows representing the many options available for each EV electric vehicle, and the stochastic charging behavior of a large numbers of EVs pose a significant challenge to the stability of the grid system. And the two part is problem and works. In order to conduct a stochastic behavior of EV user, some traditional approach to the EV bootstrapping are through aggregation as well as incentive price, which reduce the stochastic charging behavior of EVs through bootstrapping. In aspect of aggregation, someone considering spectacle and temporal distribution. Actually, the action of an incentive price, it may be difficult for EV owner uh, to charge according to the aggregation. In terms of the incentive price strategic, uh, it the previous work focus on price and through use of time, use of times of use, a data-driven approach and another dynamic approach. They put forward price strategic from the perspective of charging station income, in not the price sensitive of users. So most of previous work was done from sales side or user side without considering both perspective at the same time. In this paper, the revenue of users and the cost of the charging station will be considering considered simultaneously. So the next one is a two-level model. The problem of matching EVs and sales using incentive price pricing feature two-level structure as shown in figures 2. At the upper level, the day-ahead electricity purchase as well as the deviation between different scenarios are determined. The upper level problem, the objective function like this. The constraint consider the powers of their head and some cost, the cost of deviation. Mm. So the next one is the low level at the low level, the problem of matching EVs with sales in the real-time phrase will be solved. The objective function like this, and it have four parts of constraint. The first constraint on power, and the second constraint on the selection matrix, and the third constraint on EV SOC, and the last constraint is the sensitive of EV users. The last constraint consider the distance between the EVs and EV sales, and the lambda j denotes the price, and it can uh, it it can it can um it can derive the it can contract the EVs to chart. And the fourth part is case study. The historical data of sales are collected from four fast charging stations in Shenzhen. The numbers of charging piles of this station are set as 14, 40, 30, 35, and 40 respectively. And scenario and corresponding probability are generated using the k-means method. This is historical data of sales. This is the price of market election market, and this is the initial SOC and the initial parameters, and the as shown in figure 6, sets 2 and sets 4 power, it is the they have purchased power when there is no incentive, and remain sales do not reach the they have purchased power, and with the incentive, the powers of sales 1, sales 2, and sales 4 decrease, while the powers of sales 3 is increased. It follows that the powers of sales that exist, their purchase power will be reduced and transferred to the sales that has no complete is purchased after the incentive. In the figure 7, the cost of the four sales in real-time phrase is significantly lower after incentive. At this point, the cost of closing the graph or deviation decreased by 83.97%, and the cost of the real-time phrase decreased by 55.36%. In the figures A, comparing the challenge in the numbers of EVs at each sales with and without incentive, it can be concluded that the EV numbers of sales 1, sales 2, sales 4 decrease with incentive, while the numbers of EVs at the sales 3 increase. This correspond to the power increase of sales in figure 3. And in summary, the upper levels allows one to calculate the amounts of power purchased in the day-ahead phrase and obtain the day-ahead phrase cost. At the lower level, the use of user-sensitive price mitigate the power deviation. the total cost at the real-time phase in the therefore reduct. Additionally, the numbers of EVS and the powers at the cells where the current load exists, the their hypertrophy will be reduced. These EVs will be assigned to cells with a large power gap. In this part is the conclusion. Compared to the existing rule, the proposed method consider the coupling between EVs and cells and the relationship between user price sensitive and distant for charging side recommendation. The power of cells, the cost of incentive, and the cost of bridge, the power deviation are compared. The change in the numbers of vehicle with and without are exempt. The results indicate that operation of cells are facilitated using proposed method. The last part is future research. The future research one is the proposed method may facilitate the operation of charging station network. How to involve a detailed traffic model remain an open question. The research tool is the game relationship between multiple EV sets is also a very interesting point to study. Okay, the reference of this for this paper are shown in this slide. That's all. Thank you.